This webcast will talk about how to calculate different types of mechanical energies. When we talk about mechanical energy, we're talking about energy that a system has due to its position or its motion or both of those things. There are three primary forms of mechanical energy: gravitational potential energy, elastic potential energy, kinetic energy, and then we will also be talking about dissipated energy, which is an unusable microscopic kinetic energy, most commonly due to friction or air resistance. So first, let's talk about gravitational potential energy. That's E sub g. This gravitational energy is potential energy due to something having an elevated position. For example, the car of a roller coaster is at the top of a hill. A ball that you're holding above your head. Water that's contained in an elevated reservoir. All of these are systems where the object is high above the earth, and therefore it has gravitational potential energy. Our typical convention is that when something is on the surface of the earth or on the ground, it has zero gravitational potential energy. And then as you lift that object higher above the ground, its gravitational potential energy increases. Here are the formulas to calculate E sub g. We've got a snapshot formula on the left. This means I want to know right at this moment, when the roller coaster is at a height of 30 meters, what is its gravitational potential energy right now? In that case, when you're looking just at this moment, what is E sub g? You take the mass of the object times the acceleration due to gravity times its height above the ground. So E sub g equals mgh. But sometimes we want to talk about how has the gravitational potential energy changed. Initially it was at this height, at the end it was at this other height. How has E sub g changed? So we have a formula for the delta E sub g, that's the change in gravitational energy, and that's the weight, which is mg, multiplied by the change in height, delta h. Remember that a physicist always talks about the change in a quantity being the final height minus the initial height. In order for these formulas to give you energy in joules, you have to make sure that the mass is in units of kilograms, the height, h, is in units of meters, and of course, g, the acceleration due to gravity, is 9.8 meters per second squared. Let's consider an object that's being lifted up at a constant velocity. On the right-hand side of this diagram, we've got a very simple depiction of a force diagram for the object. If it's going at a constant velocity, then I know that the net force is zero. That must mean that the force that's being used to lift the object has to equal the force of gravity, or the weight of the object. But as the object gets lifted higher and higher, its gravitational potential energy keeps increasing. We see a depiction of that on the left-hand side of this figure. The pie of energy gets bigger, right? Its internal energy is growing as it gets higher, and the energy is stored as gravitational potential energy. If we had a diagram, a graph, of the lifting force versus the height, the lifting force is constant since it's moving at a constant velocity, and the area under this force versus height graph is telling us the amount of gravitational potential energy in the object. That force that was being used to lift the object is doing work on the object. Let's say the object is a box. So we've got a system that consists of the box and the earth. When we first look at it at position A, it has kinetic energy because it's moving upward. And when we look at it later at position B, it still has the same kinetic energy because it's still moving at a constant velocity, but it has more gravitational potential energy. That energy had to come from somewhere. It came from the external force that was acting on this box, doing and transferring energy to it by the process of working. If I wrote the energy conservation equation for this situation, I have that the initial kinetic energy plus the work that transferred energy into the system equals the final kinetic energy plus the change in gravitational energy. In this conservation equation, the kinetic energies on both sides of the equation are equal. They're the same. Therefore, if I subtract them from both sides, they go away. So I'm left with just a simpler formula that says that the work that was done equals the change in the gravitational energy. This thought experiment is how the equation to calculate the change in gravitational energy was derived. So gravitational potential energy depends on both the weight of the object and its height above the surface of the Earth. So, the weight is the mass times g, mass times 9.8. And to calculate the gravitational energy, we take that mg, or weight, and multiply by the height. So in these two pictures, on the left we have two skiers, the red skier and the blue skier. The blue skier has more gravitational potential energy because he's at a higher height. They have the same weight, they both weigh 500 newtons, but the one who's at a higher position has more gravitational potential energy. On the right-hand side of this picture, we have a red and a green skier. The green skier has a bigger weight, right? His weight is 600 newtons instead of 500 newtons. They're at the same height, but the green skier has more gravitational potential energy because his weight is bigger. Gravitational potential energy only depends on the change in height. It does not depend on the path that was taken to get the object to that height. So here we've got a picture of 3 different scenarios for how a 10 Newton ball could be lifted to a 3-meter height. In picture A, someone has lifted this ball straight up and placed it on a column that's 3 meters high. In picture B, the ball was rolled up an inclined ramp until it reached a height of 3 meters. And in picture C, the ball was taken up a set of stairs until it reached a height of 3 meters. The gravitational potential energy of the green ball is the same in all 3 situations because the weight of the ball is the same, right? It's the same ball. It always weighs 10 newtons in these pictures, and the height is always the same. So the EG, which is mgh, would be the same for all 3 scenarios. The path does not matter when you are calculating gravitational potential energy. Okay, let's switch gears and talk about elastic potential energy, which is E sub EL. Elastic potential energy is energy that's stored as a result of a reversible deformation of an elastic object. Some examples would be a coiled spring that has been either stretched or compressed, or maybe a bow that has been stretched so that you can fire an arrow, or maybe a bungee cord that has been stretched when someone their weight is hanging off of the bungee cord. There are many examples of elastic objects. These are just a few of them. When something is undergoing an elastic, a reversible deformation, then the object is storing energy until the object returns to its original shape. Now, there are a lot of objects that you can deform, but they don't bounce back to their original shape. That type of irreversible deformation is not storing elastic potential energy. Okay, so let's consider a scenario of a coiled spring, and we're applying a force and stretching it by different amounts. So the end of the spring is being displaced by different amounts. We did a lab very much like this. So when the spring is stretched just a little bit by delta x1, it has a small amount of elastic potential energy stored in it. And as the displacement of the spring increases, the energy stored in the spring also increases. And so you see the pie of energy growing. Okay. And the reason that the elastic potential energy in the spring is increasing is because more work is being done on the spring to stretch it further. So that external force that stretches the spring is transferring energy through the process of working. That work equals the change in the elastic potential energy, and so we can derive a formula for that, which is that the elastic potential energy is half of the spring constant times the displacement of the end of the spring squared. So we have two formulas to calculate elastic energy. If we want a snapshot of the elastic energy at a specific point in time, when the displacement is a certain amount, then we calculate the elastic energy as 1/2 of the spring constant times that displacement squared. If we want to know a change in elastic potential energy, for example, initially the spring was stretched by 2 centimeters, and then we stretch it to 5 centimeters. So the amount of the displacement has changed. Then we can find the change in the elastic energy as half of the spring constant times the final displacement squared minus the initial displacement squared. For these formulas to work, the standard units have to be that the spring constant, K, is given in newtons per meter, and the displacement must be in units of meter. Okay, let's switch gears and talk about kinetic energy, E sub K. Kinetic energy is energy that an object possesses because it is in motion. And so when an object is not moving, it has no kinetic energy, and when an object is moving faster, the faster it goes, the more kinetic energy it has. Here are the formulas for calculating kinetic energy. If you want to know E sub K right now, while the velocity is this amount, you use a snapshot formula, which is that the kinetic energy is half of the mass times the square of the velocity. If you want to know how much has the kinetic energy changed because the velocity changed, the change in kinetic energy equals half the mass times the final velocity squared minus the initial velocity squared. Mass has to be in kilograms, velocity has to be in meters per second. Okay, and then the final type of energy that we're going to learn how to calculate is dissipated energy. Remember that dissipated energy is unrecoverable, unusable, microscopic energy, most commonly due to friction forces or air resistance. And This is not a useful type of energy because it's a one-way trip. It's a dead end. Once energy is stored as dissipated energy, it cannot be moved, transferred into other storage modes. For example, you can't use dissipated energy to change the velocity or to change the height. We'll use these formulas to calculate dissipated energy. They're very similar to each other. So look at these. Both of these are ways to calculate dissipated energy. The equation on the top is for energy that's dissipated due to friction, due to two objects rubbing against each other. And so in that situation, the dissipated energy equals the force of friction multiplied by the path length. The path length is the distance that the object moves while it is sliding against the other object. And then the equation on the bottom applies to a situation where the dissipation is caused by air resistance. So for example, an airplane or maybe a skydiver, someone who is moving through a fluid at a very high speed so that the air resistance becomes significant. In this case, the dissipated energy equals the drag force multiplied by the path length. And again, the path length is the distance that the object moves as it is traveling through the air at a fast speed. So there are two types of forces. Some forces are conservative, and the forces that we've talked about so far that are conservative are the gravitational forces and spring forces. The reason they're called conservative forces is because energy transferred due to these two types of forces is reversible. When you have a gravitational force, so for example an object that is at a high height, you can get that energy back because as it falls, all of the gravitational energy will transfer in to other storage modes of energy. So the energy can move in and out of EG or EEL. In both cases, the path between the two endpoints doesn't matter. It doesn't matter how you got to that height. All you need to know to find the gravitational potential energy is the vertical height. All you need to know to find the elastic potential energy is the delta x, the displacement of the end of the spring. You don't care the path that the spring followed on its way to that displacement. Both of these forces, these conservative forces, are considered to be storing energy. That's why the energy is called potential, because it is stored energy. Friction and air resistance are two examples of non-conservative forces, and they're called non-conservative because the energy transfers that they cause are non-reversible. Remember, dissipation, that's the energy that the storage mode that grows due to friction and air resistance. It's a one-way trip. When energy is dissipated, it cannot be then taken out of the dissipated storage mode to be used for any other purpose. When you're talking about friction and air resistance, the amount of energy transfer does depend on the path. The further the object slides against the floor, the more friction it has to overcome, and the more energy gets dissipated. These non-conservative forces never store energy. And here's just a Venn diagram to compare and contrast the conservative forces and the non-conservative forces. Finally, there are just a couple of questions just to review these concepts. So if we have two balls, softballs, they're moving in opposite directions, but they have the same speed. One is going up in the air at 3 meters per second. The other is falling at the same speed. Of course, its velocity would be negative, right, since it's moving down as it falls. So they have the same amount of speed, but their velocities are different signs. Which one has more kinetic energy? So you might think the one that has the positive velocity has more energy, but really they have the same amount of kinetic energy. Remember that the formula for kinetic energy is half of the mass times the velocity squared. So whether the velocity is positive or negative, you get the same value when you square it. Okay, another situation is taking a backpack. You remove it from the car, you hike to the top of the mountain, then you return the backpack to your car at the bottom. Did you change the amount of the backpack's mechanical energy? No, you didn't. The mechanical energy hasn't changed because there was no real displacement, no net displacement of the backpack. The final height was the same as its initial height. It ended at the same position that it began. So the delta H, the change in the height, was 0. Therefore, the change in gravitational energy, mg delta H, would have been 0. And then the last one, a skydiver steps out of an airplane and begins falling toward the ground. So we know that their gravitational potential energy is decreasing as their height gets smaller. Does that mean that their total mechanical energy has changed? No. Remember that there are 3 primary types of mechanical energy: gravitational potential energy, kinetic energy, elastic potential energy. So in this case, the gravitational potential energy is gradually getting transferred into kinetic energy because the speed is increasing, but even though the height is decreasing. So one type of energy, one way of the energy being stored is decreasing, but it's just moving that energy into a different storage mode over to kinetic energy. They are both types of mechanical energy, so the total mechanical energy did not change.